We're now recording everything that's said from here on. Okay, now I will pause when we go to do labs or have a break or something, but then I'll try to remember to always start it back again. Okay, now, like I said, I don't have everything on Blackboard yet, but when I do get it there, when you go to Blackboard homepage for this class, you'll see a series of tabs on the left. They're blue tabs on the instructor side. I assume that's what they are on the student side. I don't get to see student side, so I don't know. In the first group, they have them in groups, sort of. In the first group, like the second or third one, it seems like says something about the syllabus and course materials or something like that. So that's where your syllabus will be. It's not there yet, but it's real close to getting there. That's your syllabus will be there. Then I think right under that is one that says instructor information or something like that. That's where I'll put my locator card. When I'm in class, on campus, off campus, not in class, office hours, all that kind of stuff. That left, whatever. Okay? That will be under that. Then go down to the next group of tabs, and one of those, I can't remember the exact title of it, it's something like, I know PPTs are in there, that's PowerPoints, handouts and more, or something like that. So under that one, I will have, now I don't have it there yet, the PowerPoints for the course, okay? Like I said, now I may not get those done tomorrow because those are on the CD and I may not have that with me tomorrow. But I'll try to get that done Monday. But I'll have the link to the YouTube videos there when I can get it done. And I think I'll be able to get that done tomorrow. There may be a few other things there, but those are most of what we've got. Okay? And then you'll be able to hear and see everything we did in the first two classes. Okay? Both of you, right? Okay. So you'll be able to catch up with that. Now, let's talk about where we are. We've already finished chapter 1. Oh, yeah. Let me do this. The first class. Oh, and let me talk about this too. When you're able to see the YouTube videos, when you go to that link, you'll see a bunch of them at the top that we haven't done. You have to scroll down till you get to the bottom, and right now there's only two in there. The first day of class and the second day of class. First day of class is just called syllabus, but I have more in it than that. The research paper instruction is there. Oh yeah, that's also going to be research paper instruction under that. PPTs, handouts, and more. That'll be under that. Okay? Research paper instruction will be there in the YouTube videos, and it'll be there just for you to read. If you listen to the YouTube videos, I go into great detail about it. So you can either read the instructions or listen to them and talk about it. Okay. So, now to go down to the bottom, the one that says PowerPoint, that's when I talk about syllabus. It says syllabus. Talk about the syllabus, the research paper instruction, my locator card, and then safety, 3 issues of safety. One we may be handling today, weather. Okay. Has anyone heard any more? I know we're under a tornado warning, but it's not a watch yet. Okay. It is a watch?
I thought it was a watch last time I heard.
Oh, which is more?
Warning is worse.
Is first?
It's worse.
It's worse. Okay, we're on the watch then. We are in the warning yet. Okay, got it. Okay, I always get those crossed up. Okay, so if we hear anything, be sure to let me know because I don't have my phone with me because I don't want it going off when I'm teaching. Okay, so all those safety issues. Then we got started on chapter 1. We finished the time. We were still working on chapter 1. Then last time, which was Tuesday, you're not in this class, are you? Pardon me? I won't be through with this class until 5:45 today. And then I'm on Birmingham campus tomorrow, probably 10 to 12-ish. And I'll be back on this campus 8 to 10 on Monday morning. Okay. All right. So, yeah, we got started in chapter 1. Then last time we finished chapter 1, We did the lab for Chapter 1, and we got started in Chapter 2. Today, it's scheduled to be, we'll continue in Chapter 2. We'll get far enough along, because we're almost there already, to do the lab in the first lab. Chapter 2 is going to have at least 3 labs. So the first lab for Chapter 2, and then the last 30 minutes is supposed to be the test on Chapter 1. Now, if you don't feel ready for the test, that's any of you, especially the 2 who just got here today, then if you want to take it later, you can, but you have to come by during my office hours, okay? And take the test on Chapter 1. But everybody should be able to do the lab on Chapter 2 today. Now, I can give you the lab on Chapter 1, but you'll need to get with somebody else to get the data and the information. Gradations here. Okay. Okay, has that brought us all up to speed? Everything we need. As far as I know, any questions? Okay, so it's up to you whether you take the test in Chapter 1. That's why I want to get the YouTube videos out there so you can at least review those before the test if you did miss the test. Oh, now the other thing, did any of you from Lab 1, did any of you need some more time with that? Because we got all the measurements done, but it was just the questions. Did anyone have any questions on those? Anything you need cleared up before you don't have to turn it in today. You always have at least a week to turn in the lab. Get them in as soon as you can. 3 people went on and turned them in last time. I'll take them anytime. Did anyone have any questions on the lab? Yes. Okay. Okay. Let me wait just a second. Let me get my copy. And I'll also give copies to the other people who weren't here last time. Okay, wait, just a minute. I'll let me get to them in a minute. Let me get them their copies so they can be looking at it. Okay, who else needs a lab? I know the 2 new people today. Anyone else? Anyone else did not get a lab last time? Okay. Now, all right. Now, the question was on, okay, and let me just say this about the lab for those who weren't here. You can listen to most of the lab on the YouTube videos once I get that link set up, but the actual measurements you have to get from a classmate, okay? Most of them haven't turned in the lab yet, so if you get with them, you can. The procedure, the directions, the instructions are all here. It's well worth a read. Even that first paragraph has the answer to at least 1 or 2 questions right there in that first paragraph, okay? And that was, part A was circles and proportionality constants. Part B was area and volume ratios. Now, after you did the measurements for part B, then you come back to number 6 here. Anytime you see a big white space like that, they're expecting an answer. And if they're expecting an answer, I'm expecting an answer. So you should be able to answer that one. You can get with people who were there. We talked about it then. Okay? Then the part C we have here. And we did that. Each team did. And then once you enter all the data and stuff, then you do a graph that's on the end of, on 6 and 7. This is on page 18. And then you answer questions about that graph 8, 9, 10, and 11. Now 11, you may want to wait till you finish everything and answer that, but please don't forget to answer. There is no wrong answer for number 11 unless you leave it blank and then it's a wrong answer. You need to put something down, whatever you think about it. Then there's results. These are based on what you did, but they're also based on your reading. Not the actual numbers you took, but based on what you learned from that, okay? And as I said before, number 3 on page 19 is very, very similar to number 6 on page 16. So if you haven't noticed that, please notice that. We talked about in class 4 and 5, both of those, I think we had examples of those in class. That was probably the first day, okay? then you read on, then problems. This is the only lab all term that you'll have problems, okay? It has problems. The first lab, why they do this, I'm not sure. But anyway, you need to work those problems. I talk about it some on the YouTube video. Now, you're asking about number 7 on page 21, right? Okay. Based on this problem, here you have an aluminum block, it gives you the dimensions, it tells you several things to do to calculate based on those dimensions, okay? What's that? No, I said, yeah, page 21. That's I thought the one you asked about. Is that the one you said? What's that? Yeah, is that number 7? Okay, right. Okay. Is it? Huh? Okay. All right. All right. It's your first day too, right? Okay. Let me go and give you the lab. This is the lab we did last time. You have to get with someone else to find out about it. It's on this page. Okay. Now you were asking about. I thought this is what I was asking you. Question 7 on page 21, right? Okay. Is that what you were asking about?
Yes.
Okay. Now that's based on the problem that starts on page 20. This problem here. This aluminum block that's 1 meter by 2 meters by 3 meters. A big block of aluminum. And then you answer questions about that block. Questions 1 and 2 on page 20. 3, 4, 5, 6, and 7 on page 21. This is all asking about that question. So that's what it says. Under what topic would you look in the index of a reference book to check your answer to question 6, which is the ratio of mass to volume for aluminum. And based on what we did in class and what we've been doing in this lab, you should be able to answer that. What's the topic with that ratio of mass to aluminum? It has a name. It was the one and only formula we had in the whole chapter 1. Okay? It had a name. Okay? Is that enough?
Yeah.
Okay.
And then
Okay.
on page 18.
Page 18? Yeah. What?
Number 11.
Number 11. That's the one I was talking about. Once you finished everything, that's the question you need to answer. Okay? There is no wrong answer for that unless you leave it blank. If you leave it blank, you don't get any points for it. Anything you answer that makes sense on that, and notice what it says. Was the purpose of the lab accomplished? You can say either yes or no, whatever you feel. And then it says why or why not. Your answer to this question should show thoughtful analysis and careful, thorough thinking. A single sentence or a couple sentences should be fine. Whatever you think about the lab. You can answer it yes or no, and then why or why not. Just, you can't give a wrong answer here unless you leave it blank. That's for number 11. So answer it however you feel. Does that answer your question? Okay. All right. So there's the first lab. Now, what do you go by? I forgot to ask you. You go by Chris? Okay. I was thinking that's what I heard, but I wanted to make sure. All right. And here's 3, right? All right. Did you hear any more about weather? Okay. All right. Now, any questions either on the first lab or what we're going to do today, first test, second lab, whatever. Okay. And again, and you're set. Slowly we're filling up here. Now, again, for those who just added the class. Now, Chris, have you been in one of my classes before? Okay, so you know about Screencast-O-Matic, YouTube videos, all that. Okay, I thought so. Okay. You can follow the first 2 classes on that. Now, we're supposed to have the test on Chapter 1 today. Unless weather keeps us from doing it, we will have that. But people who don't feel ready, that's whether you were here or not, don't feel ready for it, you can wait till later and take it, but you have to take it during my office hours. And here's Kelvin, right? Okay. So, but you have to get with me. Now, on the subject of office hours, let me say this. You'll find these on my syllabus when it's out there, on the YouTube videos when you can link it. But let me tell you now, because some of you don't have access to that yet, those that weren't here before. I don't have many office hours during the week because this is my 8th or 9th class that I'm teaching this term. So I'm in class just about all the time. My office hours are Monday and Wednesday mornings, 8 to 10. Okay? Monday afternoon from 3:45 to 6. And Friday from 8 to 12. But usually on Friday, 8 to 12, I'm on the Birmingham West campus. Okay? So if you are planning to come make up some work, like a test or something, you have to tell me ahead of time. Tell me on Thursday that you're going to be coming Friday to make up your test so I can bring a test with me. Otherwise, the test will be here and I'll be over there and you'll be over there and I will have no way to do that. So if you are going to make up a test or you need a copy of the lab or anything like that on a Friday, let me know by Thursday so I'll know to take it over there. Does that make sense? Okay. Sorry, on Tuesday and Thursday, I do have office hours from 8 to 8:30 on Tuesday and Thursday. Okay? In fact, every day I'm in the office between 8 and 8:30. However, the reason I didn't really say that for Tuesday, Thursday, for instance, last Tuesday and this Thursday, today, during that half hour, I was basically getting all your lab material up to a lab so we could do it. Okay? So I wasn't really in the office. I was setting up as much as I could the lab. We're using a biology lab, and they have classes in there, so I can't set it up until right before our lab starts. So sorry about that. Okay. Now, any questions from anyone who's been here or any of the new students? Again, if you don't feel ready for the test today, you can wait and take it, but you'll need to take it during the office hours, which aren't very many, and preferably either tomorrow or next week. Now, time out on the office hours. I just said my office hours on Fridays are usually 8 to 12, Birmingham West Campus. It's Dr. Pruitt's suite of offices, the copy room inside that. Just go in there. Rose, the secretary, will tell you how to find me. Tomorrow, a little bit of an unusual Friday, I have an eye appointment in the morning at 8:15, but it's right across the street here at University UAB West Hospital. Somewhere in there is the Branch for Eye Foundation, and that's where I have my appointment. I don't know where it is yet. I'll find it tomorrow. Hopefully, it'll be over by 9:15. It starts at 8:15. I hope it'll be over by 9:15. If it is, I should be back on the Birmingham campus by 10 o'clock. But if it goes anything past 9:15, which it easily could, I may be late getting over there. So plan, if you do need to see me tomorrow, don't get there before 10. And even if you get there right at 10, if I'm not over there, then just check with me. Hang around, ask Miss Rose if she's heard anything. She probably would not have, but if I do get a chance, I'll give her a call and let her know if there's a hang-up. I know when I'm at the Kirkland Clinic, I can't even get a cell phone service there. So I don't know about the hospital over here. They've got so much metal and electronics around, cell signals don't go very well. All right, any questions? Now, where we left off last time was example 2.2 on page 28 in chapter 2. Okay? And I'm at the speed thing. We've already covered this slide, but this gives us room to work this problem. Okay? Good deal. Thank you so much. Now, I forgot to ask of the people who came in at the beginning, did everyone get a copy of the first lab? I thought so. You just turn yours in and remind me. Okay. Now, much of the lab you'll be able to, or a little bit of the lab you'll be able to pick up listening to the YouTube video once I have the playlist set up, which hopefully will be by tomorrow. Okay. The rest of it, I couldn't record everybody's measurements, of course, on the video, so you'll have to get with someone who was there to get the measurements for the lab. And there are quite a few. So get with them, and then if you need help with calculations or questions like Dominique just had, please ask anytime. Okay. So, example 2.2. I'm going to try to model how to work these problems, because you will. This first test especially has more problems than any of the other tests we'll have all term. But there's not that many, but there are a couple or three. Okay? Most of the rest of the chapters will be multiple choice with a few fill in the blanks and maybe a couple of questions, problems. So here we have example 2.2. A bicycle has an average speed of 8 kilometers per hour. Now the symbol the book uses for average speed is V bar. Okay, that's a script V with a bar over it. Okay, average speed of 8.00 kilometers per hour. Okay, now while we're here, let me say this. I said it for the rest of it. Why didn't they just say 8? Why did they put 0.00? 0.00 indicates the precision of this measurement, which is unbelievably precise. I've never known anyone measure the speed of a bicycle that precisely. That means it's to the nearest hundredth of a kilometer per second. Wow. Okay? That would be, per hour. Hundredth of a kilometer per hour. Well, a hundredth of a kilometer is a decameter, and a decameter is not very long. It's 10 meters, so that would be about the height of the building. So in an hour you've got it to, hundredth of a kilometer, yeah. So anyway, very precise measurement. That's what the 0.00 stands for. I'll get to why that's important later. How far will it travel in 10 seconds? So they give you the time of 10 seconds, 10.0 seconds, again, a very precise measurement, and you're looking for how far. Well, one symbol for a distance would be D. That's what we're looking for. All right? Now, I'm going to go hit a tab here, which anyone can see if you go see the videos. I apologize for projector. It's been doing that periodically. It doesn't always do it, but really wobbly seeming today. There is your basic formula for speed, distance, and time. Okay? Speed is equal to distance per time. Hey, that makes sense, doesn't it? Look at this. 8 kilometers, that's the distance, per hour, that's the time. Yeah, your units are your friends. They help you see what the formula is. Speed is equal to distance per time. So I'll take that off just so you'll see. Now, I'm going to abbreviate that to do it this way. V bar, average speed, is equal to distance over time. Now, I explained this to people last time. You can either plug in the numbers to that formula, the one they gave you, or you can adjust the formula to solve for distance. I call that chug and plug or plug and chug, whatever you want to do. Which way would you like to do it? Solve for the distance first and then plug in the numbers, or would you like to plug in the numbers and then solve for distance last? You tell me. Anybody? Solve for distance. Okay, how do you do that? If this is your formula you know, And by the way, for those who weren't here, let me explain this too. Some people, for instance, when I was in the Navy, they like to use either these triangles or circles, okay? The horizontal line is called the dividing line. The vertical line is a multiplication. That's why I put the time signs in it, okay? And since you know this is your formula, D is above the dividing line. So put the D up here in either place, I don't care. And then you have V, average speed, and time. Oops, I put a vector velocity there. That's the average speed, okay? Average speed here. So average speed here, time here. So either using this or solving that for distance, what would distance be? Solving it using just the letters, multiply both sides of the equation by time. Time goes out here. What would distance be? Up here, distance would be speed times time. Speed times time. Here, canceling out the t's, distance is equal to speed times time. Okay? But, time out. Before we even do that, you see a problem with the problem. Yes, the times are wrong. I mean, not wrong, they're right, but this is in hours, that's in seconds. So, the first thing we got to do is either get this into seconds or that into hours. Well, 10 seconds into an hour is going to be a very, very small decimal, okay? Whereas, if we change this to meters per second, that's going to be a very usable term, and then you'll have your distance in meters. And they didn't say what units you could be at, but that would be how far you travel in 10 seconds. You're not going to go very much of a kilometer. It's going to be such a small number. So let's get that to meters per second. So before we do anything else, let's do that. 8.00 kilometers per hour. When you multiply this by, now these are conversion factors. And you're going to wind up with something, and we're going to have this in meters per second. So you see you've got, I put 3 conversions. You may not need all 3. But you're trying to go from kilometers to meters and hours to seconds. So pick one of those. Do you know the conversion between kilometers and meters or hours to seconds, or do you have to have something in between that? We did something like this in the last example too. Anyone remember? What's that? Okay, what in between? In between hours and seconds. Minutes, okay? So if you want to do that part of the time first, always put, I put on your conversion factors, I put 2 blanks. The first blank's always for numbers, the second blank's always for units, okay? Now, always put the units into place. Don't start with the numbers, start with the units, okay? You said we'll go from hours to minutes. So 1 unit goes on top and 1 on bottom. Which goes where? Yes? Right. Okay, it says how far will it travel? And no, you can give the answer in kilometers. You can make conversions and give them in furlongs. I don't care. Okay, but it's going to be a lot easier to get a rather big long decimal number than to have a more reasonable. And if you'll notice in the book, it does give the answer in meters. So that's the other reason I did it in meters, because that's the answer in the book. Okay, but yeah, if you got a correct answer, you get credit for a correct answer. Unless the problem specifically states how far in meters or in feet or in yards or in furlongs or whatever, then if it asks that, then give the answer in that. So we're going to start with the minutes and hours. So you tell me what unit goes where. One goes above the line, one goes below the line. Hours on top, minutes on the bottom. Now notice for minutes I put M-I-N. I don't want to confuse it with meters, which is just M. So now match the numbers with the units. How many hours in a minute or how many minutes in an hour? What numbers go there? 1 hour is 60 minutes. You got it. And notice the hours cancel out. That's exactly what we want them to do. Okay? Next. You can either do kilometers to meters or minutes to seconds. I don't care which one you want to do. You choose. Kilometers to meters or minutes to seconds. Pick one. Second? Who said? You want to do kilometers to meters, okay? You first tell me what unit goes where on the unit line. Which one? Okay, now if you put kilometers on top and meters on the bottom, notice what you're going to get. Kilometers squared per meter. Yeah, the other way around, okay? That one wouldn't work very well. See, units are your friends. They'll help tell you whether you got it right or not, okay? Meters on top, kilometers on the bottom, and that way we can cancel out the kilometers. Now, does anyone know how many meters in a kilometer or how many kilometers in a meter? You sure should. Oh, okay. What does the prefix kilo stand for? Kilo. 1,000. So it'll be 1,000 meters in 1 kilometer. That makes sense, doesn't it? A meter is about from one ear to the opposite finger. That's a meter. It's a little over a yard. And a kilometer is close to a mile. It's not quite a mile, but it's close to it. So yeah, there's going to be 1,000 meters in 1 kilometer. Okay? We still got just one to do, minutes to seconds. What unit will go where?
1 minute.
Okay, but you always put the units into place. Where do they go? Minutes on top. Perfect. And seconds on the bottom. And then what do you say? 1 minute is 60 seconds. Now your minutes go out and you're left with meters per second. And that's what we're going to have for a speed. Okay, average speed. Now what you do at this point is multiply numerators, divide by the denominators. But just to make it a little easier, I'm going to divide out a 10 here with a 10 there, a 10 there with a 10 there. So I'm going to get rid of 2 of my zeros on the 1,000. And now what we have is 8 times 10, which is 80.0 technically, divided by 6 times 6, which is 36. So if you got a calculator, plug that in and see what you get. 80 divided by 36. Anybody? Use your calculator. That's 40 divided by 18, or 20 divided by 9. What you get? 10.22. Okay. So that's going to be your speed. 10.22 meters per second. Multiply that by 10 seconds. Was that 10.22 or 2? Huh?
2.2.
That's what I thought. That didn't sound right. Okay. So this is 2.22. My hearing is bad. If you haven't noticed yet, you know it now. And we multiply that by 10.0 seconds. That's your time. And notice the seconds go out. That's important. And to multiply by 10, you move your decimal one place, and that would be 22.2 meters. How far? Meters. That's a very good answer. So your units, again, are your friends. They help you to show you whether at least your answer makes sense or not. So they got about 22 meters in 10 seconds. And that sounds about reasonable. 22 meters would be about 22 yards on a football field. And if you're casually riding a bicycle, yeah, you can easily take you 10 seconds to go 25 yards on the football field. It would take me far more than that if I was running real fast, okay, because I don't run very fast. Okay. So let's see if that's what they got in the book. Sure enough, 22.2 meters. Now they say put a block around your answer, but just so you'll be able to see what our answer finally was, that's what I got. Okay? Any questions on that? That was example 2.2. Now, they have these concepts applied in the books. Some of them are pretty nice to do. Some of them are kind of lame. This one's style speeds. If you're into that, by all means, take a look and see what you notice. I'm not going to do much on that. But the second one, the one at the top of page 29, if you're trying to estimate the speed that a stream is flowing, drop a leaf from one bridge with a stopwatch, or your cell phone usually has a stopwatch feature on it, and then measure some distance. Have that measured already before you drop the leaf. Some distance down the stream, and you know the length then, and then drop the leaf here, measure how long it takes to reach the second point, and length divided by time, that's the average speed of the stream. So that's a pretty good applied application of what we're doing here. Okay? Again, some of these are fairly lame. Some of them you might find interesting. Okay. If no questions, I'm going to remove this scratch. Is that okay? All right, to erase. Clear the screen. Because I wanted to show you the formula again that we use. Speed is distance over time. And every one of these formulas, you can get two more formulas out of it automatically, either using the circles of the triangles or just doing math with this. You can get that time is equal to distance over speed, or distance is equal to speed times time. So every time you have one equation, you automatically have two more, at least. Okay? Any questions? Okay. Now, I think we already did this average speed problem, didn't we? Yeah, pretty sure we did. And let's go on to, there's that formula again. Average speed is equal to distance over time. Okay, and they work it out. Now we're ready for velocity. Okay? Now, in everyday usage of the language, we use velocity and speed as if they mean exactly the same thing. And they are really very close, even in physics. There is a subtle difference in physics between velocity and speed. I told it to you before, but those who weren't here. Speed is what we call a scalar quantity. It's simply how fast you're traveling. Okay, speed. Velocity, on the other hand, implies not just how fast you're traveling, but also what direction you're traveling. So velocity is a vector quantity, including direction, whereas speed is just a scalar quantity with no direction associated with it. Okay? So velocity describes speed, how fast it's going, and the direction, where is it heading. Okay? And the example I gave in class, I think last time, and I'll give it again today, when I drove from home to work here today, I'm just going to make an estimate. That's about 20 miles. That's the distance. But if I want to give the displacement, that would be about 20 miles to the southeast from where I left home this morning. So it took me, let's just say, 20 minutes to get here. I'm just making a guess there. Well, 20 miles in 20 minutes would average what speed? 60 miles an hour. There's 60 minutes in a, so that's 1 mile a minute. Okay, so I was averaging about 60 miles per hour. That would be my speed. But my velocity would have been 60 miles per hour to the southwest. Okay, down southeast before southwest. Okay, when I go home, if I go on the same road, same traffic patterns, I'll probably have the same average speed. And it'll take me about the same time. But my velocity will be different. Speed would be the same, average speed. My velocity would be different because now I'm going to the northeast. So velocity implies direction as well. The graphical representation is that of a vector for velocity. Length is the magnitude. The arrowhead would be the direction. Okay? And here are the examples of this. This would be a car traveling to the east at 30 kilometers per hour. This would be one traveling to the east at 60 kilometers per hour. Notice how they doubled the magnitude or the length of the vector. The vector here's the thing with the arrows. These arrows, not those arrows. Those are just pointers. Okay? This one's also going 60 kilometers per hour, but that's going in a totally different direction, so the velocity has changed. Speed is the same between these two. Velocity is different. Velocity implies direction would be the same too. So this is definitely a different velocity. Same speed, but different velocity. Here you doubled the speed, but kept the direction, so the velocity would have the same direction, but twice the magnitude. Does that make sense? Okay. Now we're going to use this term for velocity quite a bit, so hang on to what that really implies. And here's where we're going to use it a lot, in the sense of acceleration. Now, for those who weren't here before, I'll go through this again. If you got motion, which is the title of this chapter, motion, okay, it implies two things. You've changed position from there to there. In order to move, you had to be one place, wind up at another place. The other thing that's implied with that, when you were back here, that was one time, it took you some finite amount of time to get from there to here. So you both have a distance in time, that's speed, or displacement in the time, that would be a velocity. Okay? Now, we call the velocity then, or the speed, the time rate of change of displacement or time rate of change of distance. Time rate of change. How much is it changing over time? So what is acceleration? That's the rate at which your motion changes. Well, what's another word for motion? Velocity. If you are moving, you have a velocity. Okay? So the rate at which the motion changes over time, that's the definition of acceleration. Now this can happen in one of several ways. They list three of them here. If your speed is changing, you're accelerating. So if I start slow and then pick up speed, I've just accelerated. Velocity was small there, large here, so that was an acceleration. If I go at constant speed, I'm not accelerating at all. Same speed there as here, no acceleration. Now if I started fast and then slowed down, that's an acceleration. You might call it a deceleration, but it is still an acceleration. It would be a negative acceleration. Because my final speed was small, initial speed was fast, or velocity was fast, so therefore the difference, final minus initial, would be a negative number. So that meant I was accelerating in that direction, even though I was going in this direction. Okay? That's what happens when you hit your brakes. You're decelerating. Your accelerator usually makes you speed up, your brake makes you slow down. So there's the second way that, that's all the speed change. Okay? The second way that you can have an acceleration is your direction could change. Because remember, acceleration is a change of motion, which means a change of velocity. Not just speed, velocity. So if I'm going in this direction and then change to this direction at the same speed, my velocity just changed. I was there, now I'm here. That's a change of velocity. Even though you didn't change speed, you still changed velocity. That's an acceleration. Now, so that means not only your accelerator an accelerator, your brake is an accelerator. It's just a negative acceleration. Your steering wheel is also an accelerator because it's changing your direction. Okay? So speed can change, direction can change, or both speed and direction can change at the same time. All of those are accelerations. As I mentioned, acceleration can also be negative. If you started fast and ended up slow, then it's a negative acceleration. Or if you're backing up, your speed is negative and you could be increasing your speed backing up. I'm not going to demonstrate that. I may fall down, so I won't do that. So here's a graphical expression of that. If you started at 30 miles per hour and ended up at 60 miles per hour, that's obviously an acceleration. And it's a positive acceleration. But if you started at 60 miles per hour and ended up at 30 miles per hour, now you have a negative acceleration. Because the change, remember we said motion changing. The change is always final minus initial. This would be 60 minus 30 divided by however long that took, the time. Okay? So that would be a positive acceleration. this would be 30 minus 60, which is negative 30 divided by whatever time it took. Okay? So that would be a negative acceleration. The speed is decreasing. Okay? That would be the brake. Okay? This would be the accelerator. If the direction is changing, you started at 30 miles per hour, but you're heading west, but then you made a big turn and went east, your direction is changing. So that's still an acceleration, and the acceleration, even though your speed didn't change. Now, have any of you ever been to Talladega or one of the other big racetracks? You have. Okay, what you notice about the difference between the straightaways and the curves? The curves are banked. Why in the world do they bank the curves and not the straightaways? You've got to have something pushing you toward the middle. And in order to make it bend, you have to have something pushing you to the curve and to the center of that curve. On most of your highways, I don't know if you'll notice this, you'll see they, around most curves, have also got a little bit of elevation change. Okay? You've got to have something pushing in it. Otherwise, you're counting on the tire road friction to push you in. And therefore, if the road's a little slick, icy, wet, or something like that, go around the curve too fast, you wind up off the road. Okay? There is a notorious curve. If you're coming in I-20 from the east, coming into Birmingham, right about the time it merges with 2059, it goes around like this and bends in. And that's a pretty sharp bend, and they have the warning signs and the flashing lights to reduce your speed because they don't have enough room to bank it enough. It's not a Talladega, and if you're going too fast, the unusual thing is right on the other. Does any of you know where I'm talking about there? Coming from, from Atlanta, you're just coming into Birmingham on I-20, and right about where it merges into 59. There's a graveyard right on the other side of that. I think that's pretty appropriate. If you don't slow down the speed, there's a good chance you're going to wind up in the graveyard, either figuratively or literally. I don't know which, but it could happen. So you have to have something. There is always an acceleration toward the center of the circle. We're going to talk about that later in this chapter. And here we have both changing. You come in at 30 miles per hour, leave the curve at 60 miles per hour, both your direction and speed. That's definitely an acceleration. Acceleration for a change of direction, and another acceleration for a change of speed. Make sense? Okay. Now, there's a concept here called, and by the way, they left off your formula here. I'm going to go back. Whoa, going the wrong way. I'm going to give you the formulas they give here. As it said here, the rate at which motion changes. Read motion as velocity. So acceleration is equal to velocity over time. Now again, as I told you before, I like to use a delta, meaning a change of velocity over change of time. The book doesn't use that, so I don't insist that you use it, but that means a change of velocity, delta, difference in velocity. And it's always V final minus V initial, as I've already said, over T final minus T initial. If you had a stopwatch or a clock or anything else you were doing, the initial time, the final time minus the initial time, that lets you know that time interval. Okay. And guess what, folks? That's one of those triangle things again. You got velocity up here, acceleration down here, and time down here. However, circle, triangle, whatever you want to do. And so V is equal to AT. A is equal to change of velocity over time, and time is equal to change of velocity. I like to put the delta in there, over acceleration. So you have three different formulas with that. Now, if you also have the TIs and TFs and those kinds of things, you can expand that formula even bigger And we will be doing that a little bit later. In fact, let me do it now. Let me rewrite this. Multiply both sides by that. You have V final minus V initial is equal to acceleration times T final minus T initial. Okay? Now, if you pay close attention to this, you'll notice that's a lot like your slope formula. Only rather than change of x and change of y on top, change of x, rise over run, you now have it v's and t's. But it works the same way. So what you could have here, especially if t initial was 0, then what you have is v final, let's just call that your velocity, is equal to v initial plus the acceleration times time. And that's the formula we're going to find later, if you assume that t initial is 0, okay, which is a common assumption. Okay. So I wanted to give you the formula even though they skipped it in the slides. Okay. Let me see if I can find where they talk about uniform acceleration. Oh yeah, we haven't gotten there yet. No, I know it's in the book somewhere. I just can't see it now. I was going to tell you what page it is. Does anyone see it? Yeah, I found it. On page 31, the right-hand column. Okay, we're going to get to that in a minute. So before we get there, let's go back and do examples 2.3 and 2.4. So I think I'll go to the same place we were writing here and right there. Okay. 2.3. Here we're back on the bicycle again. A bicycle moves from rest to 5 meters per second. Notice they didn't give us much precision on this. In 5 seconds. Okay? What is the acceleration? That's the unknown. Okay? Now, let's analyze everything they just told us. Okay, what do you think 5 meters per second is?
Time.
It's what?
Time.
That's not a time. 5 seconds would be the time. Okay, this is not just distance. Meters itself would be distance. Meters per second is no time is 5 seconds. Second? Velocity. Okay. Actually, in this one, probably just speed. Okay, but we'll call it velocity. So that's going to be. Do you think that's going to be your final velocity or initial velocity? Really? It says from rest to that. This will be final. Now, what in the world does rest mean? Notice several of you doing it. No, I'm sorry, I didn't say that. It's what?
Rest is not moving, right?
All right, exactly. So what would be its velocity? 0. So the initial velocity, VI, is equal to 0. Okay? The 5 seconds, did anyone decide what that was? That's your time. Now, you could call it delta t, meaning the time interval over which this happened. It doesn't mean what time of day it was. It means the time. But if you understand that, okay? Now, can we calculate the acceleration from there? What's the definition of acceleration? Change of velocity over change of time. Isn't that what we said? Rate at which motion, which is velocity, changes over time. I can't spell it. Velocity. Okay. All right. So this will be the change of velocity. That's your V final, always final minus initial. Okay. Divided by your time interval, which is 5 seconds. Okay. So this will be 5 meters per second divided minus 0 meters per second. That's your initial velocity over 5 seconds. And this would be 5 meters per second over 5 seconds. 5 divided by 5 is 1 meter per second per second. That's one way to measure an acceleration. A shorthand for that would be 1 meter per second squared. Since both of your seconds are in the denominator, meter per second is the same as meter per second squared. Now, any of you have really hot cars? I don't, never have. But a lot of times if someone's really bragging on their vehicle and how powerful it is, what will they say? It can do 0 to 60 in so many seconds, right? What are they talking about? How fast it will go? No, they're talking about the acceleration. 0 to 60, that's rest to 60 miles per hour in so many seconds, that's an acceleration. Change of velocity and a change of time. That's what they're talking about, how well it accelerates. Not how fast it can go, it can be just keep increasing till you finally get up to 70, 90, or whatever. But they're talking about how fast it can do that. 0 to 60, how fast they accelerate, how great the acceleration is. 0 to 60 in 4.7 seconds, or something like that. That may not be very good. All right, so this was 1 meter per second squared, or 1 meter per second per second. Look for this. Anytime you see acceleration, think of this. Velocity, think of this. Distance over time, acceleration, distance over time, or distance over time squared. Okay. So, and distance is just meters, or inches, or miles, or feet, or whatever. All right. Let's do example 2.4. An automobile uniformly accelerates. Now, we haven't gotten to that yet, but we're going to use it now. Uniformly accelerates from rest. What does that mean? Initial velocity is equal to 0. Okay? To 5 meters per second squared. What in the world is that measuring? Meters per second squared. What's that? Second? I can't hear it. That's an acceleration, exactly. Okay? Because those are units for it. For 6 seconds. What's that? That's your time. Okay? What is the final velocity in meters per second? So this time, the unknown here is V final. Okay, and they want it in meters per second, which will be very handy to do. Okay? How in the world are we going to get that? Any ideas? Ah, very good. If you use that formula I gave you earlier, V final is equal to V initial plus A times T. Absolutely. But V initial was what? 0. So it's just, like you said, A times T, which is 5 meters per second squared times 6 seconds. One of the seconds goes out with the second in the numerator, and that leaves us with what? 30 what? Meters per second. Excellent unit for final velocity. 30 meters per second. Exactly what the book got. Good for them. All right, now before we move to the next slide, and actually the next slide first. There is a Science and Society blurb at the top of page 31, which is transportation and the environment. It's a pretty interesting set of questions. I think be pretty good to read through, think about, and you may actually find something there that you might want to pursue as a paper topic. That's up to you. I don't, not pushing one way or another, but you may or may not. I will say this. I'm trying to remember the city it is or the country. Seems like it's Belgium or it's Holland, one of those countries. They actually have more, and of course it's a very small country. They have more bikers than they have drivers. Because it's small enough, people just ride everywhere, ride their bikes everywhere. Now, in the wintertime it's pretty cold, but they're used to it, I think it's usually not snowy and icy necessarily. That would be a little hazardous. But, man, it's a pretty good way to go. I know when I was a grad student at University of Nebraska, the apartment I lived in was about a mile or a mile and a half south of the main campus. But the main campus and the east campus, which is where my office and everything, all my research, everything else, was out about another 5 to 7 miles away to the east. So, and parking was terrible there. They charged you through the nose to park on campus. So if I ever drove, I had to park off campus, because otherwise I'd get tickets. But when the technician that I worked with was leaving, he sold me his bike, and I started riding a bike. And I could ride that just about any. Nebraska is really cold in the wintertime. I could ride the bike unless it was icy. My word, I had a couple of crashes. I didn't want to have any of those anymore. But so I tried to avoid riding in ice, but anytime else I was able to ride. In fact, I would be sweating when I got in, even on the coldest morning, because I was all bundled up and my engine was running. It gives off heat. Okay, so I would sometimes come in as sweaty as if it was summertime. It's a good way to go. And I also was in probably some of the better shape that I had been in, much better than I am now. Anyway, all right, just a little blurb for that. Okay, now let's get ready for before we get there. Now, what do we mean by uniform acceleration? Actually, that word was in example 2.4, but that was before we got to the term in the book. What that means is constant straight line acceleration. Okay? That means you're not changing direction and you're not changing your acceleration. Okay? Think of it sort of the same way we're talking about speed. If it's a constant speed at a constant direction, then you have zero acceleration. Well, now we're talking about constant acceleration, straight line acceleration. If there was a next term up there, which technically there is, but we're not going to go into it, then that would become zero then. But we're not doing it. This is what we mean uniform acceleration. Now, if you have constant straight line acceleration, that means your average velocity is simply related to the initial and final velocities in that case. If you're not accelerating at an accelerating rate, if it's a constant, uniform, straight line acceleration, if you know the initial speed and the final speed, or velocities, just take the averages. Just like if you took two tests. Take one test, another test, average them together, add them together, and divide by 2. That's all you have to do if it's uniform acceleration. The lab we're going to do today is going to be uniform acceleration. So there, our average velocity is going to be the final velocity plus the initial velocity divided by 2. Now earlier we had another equation for that. Does anyone remember what it was? Average speed distance over time. So if you can relate the two of these, you can find all sorts of information. Remember that change of displacement over change of time. That was what our first definition of average speed, average velocity. Here's the second one. Final velocity plus initial velocity divided by 2. We're going to use this concept in today's lab. So hang on to it. Remember it. Okay? Now, that leads to, let me clear my screen here and back up one more so I have more room to write. Example 2.5. An automobile moving at 25.0 meters per second. 25.0 meters per second. Now, if it's moving at that, what is that describing? 25 meters per second. Yes, exactly. Now, which velocity do you think this is? Let's read the problem a little further. Comes to a stop in 10 seconds. So guess which velocity this one is? That's your initial. Because later you come to a stop. Guess what that described? How do you say come to a stop? What would describe that? V final would be what? 0, because you came to a stop. And it said it took you 10 seconds. 10.0 seconds. So what would that be? Your time interval. You could call it delta t or just t. Okay? When the driver slams on the brakes. Now here's the assumption here. When you slam on the brakes, your assumption is your car is going to stop at a uniform rate. Because if you slam on the brakes, you're not pumping them, you're not doing anything. It's going to be a uniform force on the road. So we're assuming uniform acceleration there. That's the assumption. Okay? How far did the car travel while stopping? What are we looking for there? How far, that's your distance. That's the unknown here. Now, how in the world are we going to do this? Because to get distance and time, you need to know average speed, don't you? We don't have an average speed, or do we? Huh? Yes, average them together. Add the two together, divide by 2. Okay? So your average speed, V bar, is equal to 25.0 meters per second plus 0 meters per second. Yes, divided by 2 is 12.5. What units? Meters per second. When you add, you're not, or subtract, you're not, you don't change the units. 12.5 meters per second. Now, how would you get your distance from that? Remember the other formula for V bar I just gave you? Is what? I don't think so. Okay. Give me the basic formula. V bar is equal to, what's that? D over T. So if you're solving for D, what would it be? D over T. No? If D is V is D over T. Okay. D is what we're looking for. Is V times, yeah, okay. That's it. V bar times time. So that would be your 12.5 meters per second times your 10.0 seconds. And that would be, here the seconds divide out, which is good. That gives you 125 meters. Okay? Now, 25 meters per second doesn't sound all that fast, does it? It actually is going at a pretty good clip. That's going pretty fast. We could go back and find out how many miles per hour that is. That would take a lot of conversions. Let's not go there now. That's going pretty fast. You slam on brakes, and it takes you 10 seconds to come to a complete stop. You have traveled about 1 1/4 football fields. Okay? That would be from the outside of the end zone here to the goal line, to the other goal line, to the other end zone, and then another few yards on out there. About where the flagpole is, you know, in those footballs. Yeah, you have gone a long distance. And not a huge rate of speed, but yeah, that's why you don't tailgate, folks, okay? Because if something were to happen up there, if you're too close, no way you're going to stop. No way. Okay. Now, let's see what they got. 125 meters, good for them. All right. Now, there's the second question, 2.6. I'm glad I didn't erase this, because 2.6 then asked for what was the deceleration of the automobile in example 2.5. So what's the acceleration? What was that formula? Anyone remember? Okay, change of velocity over change of time. Okay? I like to put those deltas in there, the book doesn't. This is velocity final minus velocity initial over the time interval it took, and in this case that was 10.0 seconds. So what was our T final? Our V final? 0 minus V initial? 25.0 meters per second, all divided by 10.0 seconds. And that would give you what? I'm going to have to write up above here. When you divide by 10, you move your decimal one place to the left. That would be a minus, your acceleration here would be a minus 2.5 meters per second squared. Yeah, meters per second squared. Meters per second, which is a minus 2.5 meters per second squared. That's a pretty healthy acceleration. Okay, a lot of times accelerations are much less than that. And they got, oops, ha! They caught me. There were 3 significant digits everywhere, but when I did my subtraction and division, I forgot to put the other 0. Usually, if all your inputs are 3 significant digits, give the output as 3 significant digits as well. Now, I don't count off if you don't, but I'll usually mark it. That's where you go. Okay, there's another concept supplied, which is a acceleration pattern. Again, maybe a little on the lame side, though I have heard of a pretty good experiment that some physics classes have done before, and this is pretty nifty. They got a car on flat level parking lot, and they keep people from driving through it, and they put 2 or 3 people in the back of it pushing on the car, but pushing on scales on a car. So the amount of the push they're doing is measured in pounds on the scales, okay? So that gives you, what we're going to talk about later, a force, okay? And somebody sitting inside the car, the lazy bum, is every second putting out a marker. It could be a little bitty traffic cone. It could be spraying some paintball or something like that on the thing. And as you're pushing, you're registering. You add up the forces by which the 2 or 3 people are pushing, and then those are the forces. You can measure your acceleration by measure your speed, change of distance per change of time, that's your speed, change of speed per change of time, that's your acceleration, and then relate their acceleration to forces, which we're going to do a little bit later. It's a pretty fun experiment, but we don't have very many level parking lots. We don't have any that we can close off and not have people driving over them, so I don't usually do that. All right, so let's move to the next topic here, which is forces. Okay? Now they're going to go way back in time, Aristotle. Now, Aristotle was a dude that lived, it seems like something like 200 or 300 years BC, before Christ. So this is way back there. Really famous Greek, what they call a natural philosopher. He observed nature, he philosophized about it, and wrote things. And frankly, he was top of his class. He was an expert. Everybody respected Aristotle. So basically, if Aristotle said it, no one questioned it. And that happened for thousands of years. Everybody, if Aristotle said it, they believed it. Even if they were from different cultures, different areas. Yeah, I'm not sure the Chinese paid any attention to him. They didn't even know about him. But Western culture. Okay? Here was one of his statements. Heavier objects fall faster than lighter objects. Does that sound reasonable or not? It does sound reasonable, doesn't it? Okay? Heavier objects fall faster than lighter objects. Okay? And everybody pretty much said, yeah, that sounds right. Yeah, we'll believe it. We'll go with it. Well, here came, and here's another one. Objects moving horizontally require constantly applied force, or otherwise they stop. Yeah, that sounds pretty reasonable too, doesn't it? Okay? Most circumstances. Aristotle sounded okay. Okay? But he basically relied on thinking alone. He observed nature. He was a really good observer of nature, and then just thought through things and said, yeah, this must be it. Okay? But along came Galileo. This was close to 2,000 years later. Okay? Maybe not exactly, but fairly close to it. Between 1 and 2,000 years later. Closer to 2, I think. Along came Galileo, and then in the next generation, Isaac Newton. Galileo was from down in Italy, Pisa, Italy, P-I-S-A, where they have the famous leaning tower. Okay? And it's so bizarre. The very year that Galileo died, on Christmas Day of that year, Isaac Newton was born. Sort of like they did a tag off, the way up and down water. I'm just making that up. Okay, so anyway, Galileo and Newton came along, and Galileo said, no, I think all objects fall at the same rate. Really? Galileo, are you serious? Aristotle didn't think that. Okay? No force is required for uniform horizontal motion. Uniform horizontal motion. Same speed. Okay? Aristotle said, yeah, you have to apply force, or actually it'll come to a stop. And what Galileo did, and later Newton, they reasoned things out, but they based them on an experiment. Now, I can't say for certain that this is one of Galileo's experiments, but it will define that. These two pieces of paper, basically, would you say are pretty close to the same weight? Yay or nay? Yeah. You think they're about the same weight? Make sure I get the right one. Yeah. Okay. So, would you say they should fall at the same rate then? Yeah, pretty close. You would think, right? Same weight. Same weight, right? That fell much faster. So it's not the weight that makes the difference. It's something else called resistance. This one had a bigger surface area, same weight, bigger surface area, so it had more air resistance than this one did. So this one fell faster. And basically, that holds for just about everything. Heavier objects don't fall faster. It's just that a lighter object will usually meet more resistance sooner. Okay? So that's what the difference is. And that same thing holds here. We roll a ball down a path, whatever you're doing, horizontal path, in time, that ball will come to a stop. Okay? But, picture this. Let's say that surface now is perfectly slick. Just a perfectly slick. Roll the same ball down that, is it going to stop as fast? No, because it's well lubricated, for instance, okay? Not having no resistance, less resistance anyway. So therefore, no force is required for uniform horizontal motion as long as there's no opposing force as in friction or air resistance or something else. And Galileo reasoned this out. Aristotle had just thought through it and said, yeah, it looks like things are this way, and based it all on that. Okay? Now, I actually did, for one of the first times I taught physics, we didn't have a lab in the class. So what I did, I just did a demonstration. I found there is in the lower part of this building, the part that has 3 floors, okay? The lower part of the building, there is an old stairwell there, somewhere packed in the corner. I got them to unlock it for me, because they keep it locked up all the time. And I went up to the top of the stairs on the 3rd floor, and there's a window there in the stairwell, and opened the window and leaned out the window and had my class down on the grassy part down the base 3 floors down. And I had a 1 kilogram, 1,000 gram weight, and a 1 gram weight. 1,000 times heavier. I dropped them, they landed at the same time. And supposedly this is what Galileo did when he went up on the Tower of Pisa. Whether this is actually true or not, we don't know. But he went all the way to the top and has his assistants down on the ground below measuring how long it took the things to fall. Heavy rock and a light rock. Okay? Big rock and small rock. Many times heavier than this one. Did at the same time. He was many, many floors up. Still fell at the same rate. Because they met just about the same air resistance. Okay? So, note. Galileo, Newton, they did experiments and tested things, and they changed a lot of the things Aristotle had always said was true. So what is a force? Now, I remember I took physical science my freshman year of high school. Everybody did pretty much. And most of us in the class were scared to death because the teacher for that high school class was the football coach. And his name was Pooley Hooper. I don't know what his real first name was, but they called him Pooley. No one made fun of that either, okay? He had played football at Alabama. He was old by the time I had him. It was in the last few years coaching, in fact. He played at Alabama. I think that was even before Bear Bryant, okay? But he was a tough old nut. He was on one end of the other of the longest pass in football in the Rose Bowl history. I don't remember if he threw it or he caught it, but he was on one end of that. He was a tough old nut. And I can remember him saying, he talked just like Bear Bryant, so I would have thought a dwarf is a push or a pull. You know, to this day I remember him saying this. So that's exactly what our book says, a push or a pull. But a push or a pull capable of changing an object's state of motion. Now, what do we mean by state of motion? There's another word for that?
Force.
Not force.
Acceleration.
Okay, velocity. Changing an object's velocity. A force is a push or a pull capable of changing an object's state of motion. Think of that, velocity. Now, the overall effect is determined by the vector sum of the forces. We call that the net force. Now remember, forces are vectors. We didn't say that, but they are. Velocity is a vector. Acceleration is a vector. Displacement is a vector. Forces are also vectors. And they give a couple of examples here, at least in this figure here. And this really cuts home to me. This looks a lot, it's a cargo ship, is exactly what it looks like. These are booms or rigs that they use to load and unload the cargo. But that looks an awful lot like one of the ships I was on in the Navy, or an older version of it, it was an ammunition ship. Just another little side note that's not at all important for the class. Ammunition ships are named after volcanoes. Not too surprising, because if you ever have a fire on an ammunition ship, you're going to leave a big hole in the water, okay? So they were one of the safest ships you could be on, because everybody was very fire conscious on that. Nobody did anything to risk that. So this is a ship, and I can remember being on the bridge when we went into San Francisco Bay. We were stationed out there. And once you get in the bay, in fact, before you get in the bay, they bring on a harbor pilot, and they bring tugs out for you, because you can't maneuver a big, heavy ship very tightly in a very constricted waters like that. So this shows this cargo ship being coming in, and they're going to put a couple of tugs behind it. One tug is going to be, well, not behind it, on the side of it. One's pushing with 1,000 units east, the other's pushing with 1,000 units east, because we're trying to get this ship to turn real quickly without taking a lot of distance to do so. Okay? The net force that the tugs are exerting on the ship is 2,000 units to the east. Remember, forces are vector quantities. You have magnitude and you have direction. Okay? But what if someone got their signals crossed and one tug was on one side and one tug on the other side? They couldn't see each other, and they both started pushing with 1,000 units to the east, but the other 1,000 units to the west. They're going to sit there and go and not move anywhere and say, what in the world is wrong? Because the net force is now zero. Even though they're both applying a force, but a force is a push-up pull capable of changing an object's state of motion, the net force would be zero, because it's not changing the motion at all. Okay? But what if you had a... Boy, they got this wrong. Oh, no, okay. They had one tug, a little tug over here pushing with 1,000 units to the east, but on the other side, they couldn't see it, was a big old tug pushing with 2,000 units to the west. What's the net force on that? Poor little tug on this side, the ship looked like it's coming on top of him. It's not, it's just pushing him, because you have a net force of 1,000 units to the west. Because you add both magnitude and velocity. These add to zero. This is 2,000 west, but it only winds up with a net 1,000 west, because you had 1,000 to the east, canceling that out. Now, there's other examples of this. When we moved to the house where we currently live, one thing we really liked about it were all the trees in the yard. The first house we lived in Birmingham was the first house we bought, not the first house we lived in. The first house we bought had basically no trees to speak of. The house next to us had a tree. We got a little shade from it, because the houses were pretty close. On the other side, well, back in the corner, there was a tree that gave us a little shade, but we weren't ever back there. So we planted a few things like crepe myrtles and stuff, which are more ornamental than they were for shade. But when we moved to the house where we currently are, it's in, by the way, Forest Park. There were trees all over the place, and I really liked the trees. However, they had let too many trees stay there. There were two really thin, spindly pine trees growing up in an oak canopy, which big old oak trees, and they were trying to reach to the sun, so they were crooked, ugly little trees, trying to reach up to the sun, bent and curved and stuff, and they were just not very good trees. There was also a maple, but there were these two pines. Well, my father-in-law and his other son-in-law came down from Huntsville, bringing my father-in-law's chainsaw and some wood. And what we're doing, because our yard, it's a good-sized yard, but we didn't want it falling and hitting things we didn't want to do, so we wanted to guide the tree down, my brother-in-law and I, guiding it down while my father-in-law was chainsaw. And so we threw as high up in the tree as we could, because it was a long way up there until you got the first limb. We finally got it over that first limb, brought it down. Now, the maximum force we could have done if we would have both pulled in the same direction. and then pulled it this way while my father-in-law cut it. What would have been wrong with that picture? If we were both pulling side by side this way, maximum force we're exerting on the tree to get it to fall the way we wanted it to, what's wrong with that picture? The tree's going to fall straight on top of us, okay. So we chose to go at an angle. He pulled that way, I pulled this way, with where we wanted it to pull down the middle. Did we have as much force pulling on the tree? No. Well, the total forces were the same, but you see, he was pulling this way, I was that way. And here's how you talk about forces, okay? This is a little too simple here, okay? If the tree was here, and he was pulling this way and I was pulling this way, we had vector sums. Part of this was in this direction. That was his force and my force there. But part of the force goes this way for me and that way for him. Well, guess what? These two forces cancel each other out. So we're pulling against each other to some extent, sort of like this was. But the other two add, and this is how you add. This is called a vector sum, okay, or a net force. It's not as great as the two forces were, but the components add, not the total forces add. And sure enough, the tree fell down in between us, just where we wanted it to go. Not as good a force, but we didn't have the tree on top of us either, so we were happy campers. Okay, how are we doing on time? Okay, we go till 3:15 today because we have a lab that's 2 hours, and then the test, which it probably won't take you 30 minutes, but I always give you at least 30 minutes to work on the test. What's that?
How many questions?
It's only 10 questions, but there's multiple parts.
Okay.
So it's going to be a total of about 18 parts. Okay. This is the only test that way. Later, if there's 19 questions, there'll be 19 questions, not multiple parts. Not every time, but a lot of times. Most of it will be that way. Today is a different kind of test because the test bank was just terrible questions. Okay, so there's what forces are. There are 4 what they call fundamental forces of nature. Now these are not forces like pulling on a tree, okay, pulling on a rope. Not those kinds of forces. These are the fundamental forces. The most basic of all interactions. The first of these is gravitational force. Has anyone here ever experienced gravitational force? You are right now. You're not floating up into space. You're not sliding around somewhere.
It's air, right?
Huh?
It's air. What's gravitation?
Gravitational force is a mass interaction between any two masses. It's a very weak force, though. You have to have a huge amount of mass before you sense gravitational pull. For instance, the Earth. I can jump up, I can't jump, but I can throw something up, as in a ball or something like that, and it's always going to come back down. I can't ever throw it fast enough and hard enough that it escapes Earth's gravitational field. They always come back down. Okay, but not only that, all the planets, not just Earth, the moon, the sun, stars, everything, galaxies, all this is determined by these gravitational forces, the motion. Because these are big, huge bodies that pull on things. Okay? See, I can't tell any gravitational attraction between me and the desk here. There is some, I can't measure it. It would be 10 to the minus 33 or something. It's such a small number you can't detect. Now, next strongest beyond this is electromagnetic forces. Now, notice there's both electric and magnetic involved there. These are usually charged interactions. Okay? That's both electricity and magnetism. Magnetism usually, we don't talk as much about charge as we do magnetic fields. But this is what holds together things in chemistry. We'll be talking about this later. Atoms and molecules in chemistry. Now, it's usually stronger than an equivalent gravitational force, but a gravitational force will act over a far further distance than electromagnetic. So even though this one's stronger, it doesn't have the range of a gravitational. Now, how you know it is stronger, one of the sort of classic examples, if you got fairly clean, dry hair on a dry day, and you have a rubber comb. Now you have to have enough hair. I would call it's not that funny. Now, enough hair, and you comb your hair real briskly with a rubber comb, but then have little pieces of paper torn up onto this. Have you ever seen this? And then hold the comb down here, and the paper attaches itself to the comb. And sometimes we have a daisy chain of little pieces of paper. Okay, that's electrostatic forces. And why do you know it's stronger than gravitational? Because those pieces of paper, gravity's pulling them down, the electrostatic's picking them up. So it's a much shorter range. You hold the comb up here, where the paper, you hold it here, they're going to go down. So it's a stronger force, but doesn't have nearly the range. Now these next two physicists must have named because they're really lame names. Weak forces and strong forces. Yeah, right. What a weak force is a force involved with certain nuclear reactions. I can tell you this, if it's involved with a nuclear reaction, it's not very weak, but it's weaker than the strong forces. Okay. Now, I can't tell you much about the weak forces. It's sort of hard to describe. But I'll tell you about the strong forces. Okay? You know what an atom is made up of? There's three parts. We touched on this last time. What were they?
Electrons.
Electrons, which are what charge? Negative charges. Okay. That's what, by the way, atoms and molecular chemistry, that's all based on electron. Yeah, okay. And next were protons and neutrons. Protons are positive charge, neutrons have no charge, neutral charge. Okay. Now, the protons and the neutrons all live in an incredibly tiny little nucleus. And almost the whole mass of the atom is in that tiny little nucleus. Protons and neutrons are all in there. Protons are all positively charged, and neutrons have no charge. Yet they're packed in there in an incredibly small nucleus. Now the electrons are out here flying around. They have almost no mass, like 1/10,000th amount of mass of a proton or a neutron. So almost no mass, but they're flying around. They take up the whole volume of the atom, which isn't very big, but I'm making it look big. But the nucleus has all the mass. And think how close those protons are to each other. And yet they're all positively charged. Now, electromagnetic forces would say they should be repelling each other like crazy because they're the same charge. But no, they're being held in, what? By some strong force that holds that nucleus together. Now, we don't understand that, or at least I don't totally. Quantum mechanicists, or whatever you call them, they have a lot better field of it, but who understands quantum mechanics anyway? I mean, really, those strong forces have to be incredibly strong to overcome these magnetic forces. I mean, really powerful. But they don't go for very far. They're incredibly fast, strong, but their distance, their range of influence is basically that nucleus. They don't extend beyond that. So again, a much stronger force than electromagnetic, but doesn't reach nearly as far. And that electromagnetic is stronger than gravitational, but doesn't reach nearly as far. So those are your four fundamental forces. I'm trying to think if the book says more about the weak forces. I don't think it does. I don't even see where it says anything about it. Yeah, here they are. And these cannot be explained in terms of any other forces. They stand on their own. Here's all they say in the book. Weak and strong forces act inside the nucleus of an atom, so they're not as easily observed at work as our gravitational. The weak force is involved in certain nuclear reactions. That's all it says here. The strong nuclear force is involved in close range holding of the nucleus together. That's all they say. In general, the strong nuclear force between particles inside a nucleus is about 100 times stronger than electromagnetic forces and about 10 to the 39th times stronger than gravitational forces. So quite a big difference. Okay. Now, basically, what we did before forces is going to be today's lab, okay, which will be starting in about 10 minutes, okay? The stuff I just talked about will be part of the second lab for this chapter, which will be next Tuesday. This next part is more of what we're going to be doing in next Tuesday's lab. So we'll have class, we'll have class for 2 hours on Tuesday, so we'll get all this covered by then. But let's go on and cover what we can now. Horizontal motion on land, okay? Remember, good old Aristotle said that you have to keep adding a force to keep an object moving horizontally. And most observations would support that, okay? But what he didn't take into account is that there were opposing forces. That's what's slowing the ball down. It's not that you need to keep applying force, it's there are opposing forces. So here's what we have here is you have a ball rolling. Okay, now this picture is hard to picture. The motion is this way. Believe it or not, the motion's this way. You start a ball rolling. Think of it as a bowling ball. Okay? You start it rolling. You roll it down the lane. Okay? I always wind up in the gutters, but imagine you can stay in the lane. Okay? So it's rolling down the lane. Now, if the lane were really, 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 really long, eventually that ball's going to stop, okay? And why is that? Because once the bowling ball leaves your hand, you're not applying any more force to it. But as it's rolling this way, you've got air resistance that's opposing that. Now, it's a sphere, so that's not a huge amount of air resistance, but there's some. But you also have friction. Because if you've ever been in a bowling alley, you know how loud it is, right? Because anytime there's making that much noise, there's got to be friction. Noise is vibrations, okay? So there is friction between the floor. So there's frictional forces resisting the motion. There's air resistance resisting the motion. These add up, your net forces in this direction, because once it left your hand, you don't have any more forces on it this way. And that's why Aristotle thought you had to keep adding forces or else it's going to come to a stop. Well, what he didn't take into account were there opposing forces there. If you had no net forces on it, it keeps going forever. Very seldom do you have that. Okay, now you're applying a force in this direction. And if that force is exactly the same sum of these two opposing forces, now we have zero net force. But if it is moving this way, it never stops. Okay? Because a net force on it, anything negative or positive, is going to change its motion. It's going to change its velocity. It's going to accelerate positively or negatively. This was a negative acceleration. This is a zero acceleration because in this case, the net force is exactly zero. The applied force is exactly equal to the two opposing forces, and so therefore it's going to be a net force of zero. Now, natural motion that Aristotle was talking about is a continuous force necessary to keep an object moving. No, if there's no unbalanced retarding forces. Okay, very seldom do you have none, but they have had one example that I can think of now. I think I described it to you before. One of the moon missions, when they landed someone on the moon, they walked around. It wasn't the first one, not Neil Armstrong, but one of the later ones. They took a hammer and a feather and dropped it. And guess what happened? Fell at the same way. On Earth, the feather would have done this thing. That's why Aristotle saw, but what he wasn't taking into account was the retarding force due to air resistance. But on the moon, there is no air resistance. So they fell at exactly the same rate. Okay? So, no, in the absence of unbalanced retarding forces, nope, there are no continuous forces necessary. Now, this is something that Galileo contributed. and we'll get to it later, but it's the concept of inertia. The measure of an object's tendency to resist changes in the motion. That even includes rest. Now, usually when I think of inertia, I think of something being inert, meaning not doing anything, okay? Just there, okay? Sort of me on a Friday night. Goodness gracious, I'm so tired by then, I just want to collapse, okay? But inertia really means the measure of, in fact, if you think of this, N means no inertia, okay, no movement. But actually, inertia means an object's tendency to resist changes in its motion. That including rest, by the way. So let's say that I had that bowling ball I was talking about, and I'm going to rear back and roll it just as fast as I can toward you, okay? In order for you not to get hit, you're going to have to change its motion, kick it or do something like that. My guess is that's not going to feel very good, okay? Because that bowling ball has a lot of tendency to resist the change in motion. Now, if I did the same thing with a ping pong ball and rolled it just as hard as I could at you, no problem at all, because it doesn't have as much inertia. Not nearly as much. So, very little tendency to resist changes in its motion. Okay? So, that's kind of like, well, there's lots of other examples like that. That's probably enough of that. Okay. And that also includes being at rest. If that bowling ball was at rest, I decided to kick it to make it move somewhere, that's probably going to hurt my foot pretty much too, right? But if I kick a ping pong ball, I'm not even going to notice I kicked it, you know. It's just going to go, okay? Again, even at rest, the tendency to resist a change of its motion. That's a measure of inertia. We're going to talk about, that's what inertia is, a measure of that. We're going to talk about how we describe that measurement a little bit later, but hang on to the concept. This will be in the next lab. 2 labs from now we'll talk about this. Okay. So let's talk about balanced and unbalanced forces. How are we doing on time? Just a few more minutes. Let's see if we can get this one done. Okay. There's hardly any place on the surface of the earth you're not going to have some unbalanced forces. There's always air resistance, there's always friction, there's always something. But if you get up into outer space, the moon would not do bad, but outer space, there's natural motion in free space, constant velocity. You don't have to be, pumping on gas or anything else. If it's going, nothing's going to change it. There's no air resistance. If you're way out in outer space, there's no even gravity that you're pulling against. Okay? So motion continues unchanged without those unbalanced forces. The retarding forces will decrease the speed. A booster will increase the speed. A sideways force will change. Here's what we mean. What if that satellite was out there, but you fired some what they call retro rockets? Or, say, a chunk of space junk comes and hits it. That's going to that force that is hit by, or the force of the retro rockets, are going to slow it down and make it move, if not move in the opposite direction, decrease the motion in that direction. It's going to go like this without any change unless something forces it to change. So an opposing force will slow it down. If, however, you boost the rocket, in other words, in the same direction it's already going, just give a little spurt of rocket, it's going to speed up, accelerate until you turn that off, and then it's going to go to the new constant speed, whatever it's increased to. So that boost is needed to increase the speed. However, if you happen to have a force in this direction, it's not going to change the speed any, because it's not coming from here or here, it will merely change its direction. But it's still a force, that's still an acceleration because you change the velocity. Okay? Not a decrease in velocity, not an increase in velocity, change of direction of velocity. So that will happen if your unbalanced force is at an angle, preferably 90 degrees, that's all it'll do. If it's a little like this, it's going to increase the speed and change direction, A little like this decreases speed and change direction. Like this, it's just going to change the direction. And by the way, that's what the sun does to the earth. That's what the earth does to the moon. Because we're traveling this way, the sun's pulling us this way, that's what keeps us in a circular path. If it pulled too hard, we'd spiral down and burn out. If we were going too fast, we'd spin out of control. But we're balanced, okay? And thank goodness we are. And by the way, y'all have cell phones, GPS in your car or something like that? Those satellites, they're fixed in space. They never move over where they are. That's why you can know exactly where you are. If they were moving one way or another, you'd have no way to accommodate them. They're in exactly fixed orbits. Okay. All right. I think we're close enough to time. Yeah, is that right? Okay. So horizontal motion, that's what we've been describing. We're going to pick up next time with falling objects, which is vertical. Okay. There is a dumb little mistakes and misunderstanding in the text. If you walk or run in the rain, which do you get wetter? Say again? You get wet in both, and that's really the best answer. If it's the same time you're out there, you're going to get the same amount because the rainfall doesn't depend on whether you walk or run. Where you get wet, if you're running, you're going to get more wet on the front side and less on the back side. It's just like when you're driving in a car, you have your front windshield wipers on, but most of the time you don't need the back on because the rain's not hitting it. Right? Okay, so to me, some of these are sort of lame too. So anyway, we will go from there. I don't know what I did. Oh, there it is. Okay. And pick up there next time. We have almost, not quite, for Tuesday's lab, we got to do vertical motion, falling objects, and compound motion. Then we'll be ready for the next lab. So we'll get that done in the first 2 hours easily. We'll probably get into 3 laws of motion too, which is good. We'll get that done too. There'll be one more lab after that. So this is a long chapter, a lot to cover. So I'm going to pause this. All right. If you have a copy of the lab, this one doesn't have nearly as much to read as the others do. Sorry about that. But what you're to do first, now there's only 2 scales. Oh, we need to divide up. Okay, let me get my roll book again. Let's see if everybody's here, because it has grown since the last time. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Missing 1. 5, 10, 15. We're missing 1 person. Darna's here. Dominique's here. Or is she? Dominique. We lost Dominique, right? Okay. So we're down to 15. All right. So what we'll do, there'll be 5 people on each team. So if one of these people can go join that team, I'd appreciate it. Okay? Yeah, this one over here. All right. Good deal. So we got 5, 5, and 5. Okay? And as you may have guessed, it is a fairly short lab today, fairly straightforward. Okay. We've only got 2 scales, so y'all are going to have to share. Each team has 3 balls that they're going to be using on the inclined plane. 1 metal ball, 1 ping pong ball, which I'm calling plastic, and 1 rubber ball. So each team has 3. Okay? If you'll come, place them one at a time on the scale, but before you do, be sure you zero the scale. Okay? Watch it. Okay. Be sure you zero the scale. Now, if you have trouble keeping the ball on the scale, then you can use the weighing tin. But if you use the weighing tin, you have to zero the scale with the weighing tin on it. So always zero before you take a measurement. So all three teams measure your three balls. The plastic, which is ping pong, will then use the weighing scale. Okay, but you have to zero it with that. Zero it with that on.
Oh.
No, put that on. Zero the scale now. Okay. Okay. And every one of the little bitty lines there is 1 gram. Okay. All right. All three teams in time get all three scales. While y'all are doing that, I'm going to set up the next part for you. No, this is my problem group, so let me get yours set up first.
Problem group.
Oh, I'm sorry. Did I say that?
On 5 degrees.
Yeah.
I had to set up.
Oh, look at that. Well, why isn't it anymore?
Because Grayson been touching it.
I
was trying to.
Okay.
I think I'm cool
By the way, you're absolutely right. The line at the bottom is what the problem is.
And you call us your trouble group.
Oh, yeah. Okay.
like this, like 4 grams, centimeters.
That's grams. No, just grams.
Yes, it
Yeah.
is. Trouble group right there.
Yeah, I believe you're right. No, I'm just kidding.
Or that fall on any of them side of the
I want your teachers to notice the long line at the bottom, that's the one you measure this by, not the one on top, the one on the bottom. That's sacrifice. You're not going to measure it yet. Okay. Okay. As soon as the scale gets free, let me know so the other team, the other team can come and use the scale.
So the plastic was 4 grams.
Got it. You third. The scale's free.
Yes, sir, boss.
All right.
You need the ball.
Okay.
I'm not on this one. I'll be honest.
Wait. Okay. You zero the scale before you put the ball
Oh.
I believe that.
So,
on. So that way you're measuring only the mass of the
mass
ball.
of. Okay, I thought you were acting.
Millimeters.
Yeah, all right.
Oh, I'm sorry. All right, very good.
Say 2 grams.
We all still working on it. Okay. Y'all having any trouble with them rolling off?
Good, you're good. You're great.
If you need a weighing tin, there's a weighing tin.
66.
Need a weighing tin? Okay.
We good.
Oh, you're good. Okay. Now, the next thing that you measure is measure the length of the track here. And that's from inside to inside, and do it to the nearest tenth of a centimeter. Okay? Your tenth of a centimeter. Did you get all 3 balls measured?
Yeah.
Okay.
Everything's great.
Looking good. Thank you.
Looking good. All right.
Okay.
I'm doing it with this ruler again.
Okay. Now, turn it up so it's the meter side up. That side.
This side, yeah.
Okay. And measure with the 0 on that lower end. Okay. Inside.
Inside.
And you might want to tip it up like this so you can read to the nearest tenth of a centimeter. The inside to inside.
43. Hold on.
Y'all got the 3 measured? Already did that? Okay, super. Okay, now, each team also has a stopwatch.
46.
Okay? Now let me describe, it's real simple, the use of the stopwatch and what not to do. Okay? At about 1 or 2 o'clock, you'll see the start stop. Press it, it started. Press it, it stopped. That was 1.62 seconds. The big number is the number of seconds. The little number is the hundredths of a second. Okay? Now to reset, go over here to 10 o'clock. Press that, and it should go back to 00. Now yours looks like it's a 7 here. It's just that you're not going to have anything that's the number of minutes. You're always going to be in seconds. So that doesn't bother it. Do not hit the middle button, please. That changes the scale, and I have to go through and figure out a way to get it back to the stopwatch mode. That changes the mode. Don't hit the middle button. Just start stop is on the right, and reset is on the left. Okay? Now, what you do then, has everybody got the length measure? Okay.
Yeah.
What you do then, but the thing set at 5. Okay, now listen up, folks. Okay. Before you start taking your measurements, listen up. Okay? Now, what you're going to do, if you read this, what you're going to do is measure the length of time that it takes for the ball to roll down the ramp. Okay? You're going to release it from rest, and at that moment you release it, start the stopwatch. I would suggest the same person with the stopwatch release the ball, so you don't have any delayed time. You know exactly when to release it. Don't push it. Don't throw it. Let it start from rest. Now, do not put the time in the column over here under time. Write it on. Write it on the back of either the previous page or that sheet. Because what you're going to do is take 3 measurements of each ball at each elevation. 3. Now, you have 2 options here. One is to average, which takes a while. I'd suggest take 3 measurements, throw out the high, throw out the low, just use the middle value. It's going to give you pretty close to the average anyway. So take 3 measurements. Now, if one of those measurements is way out of kilter with the other, the stopwatch didn't work properly, your thumb didn't work properly, something didn't work properly, then discard that one and do another one so that all 3 of your times are very close to each other. Then throw out the high, throw out the low, and you use the middle one. Does that make sense? So that's why I say write your times on the back, either of that sheet or the other sheet, so that then you can record the time. The middle time is what goes in the time column. It is a time, but it's not every time. Just that. Any questions on that? Okay. So do 3 measurements for each ball at each elevation. Okay? And what I would suggest is whoever is releasing the ball, do it. The others of you record the time when that person calls it out. Okay?
Oh, how you stop the thing? Like, this going to start, and how you stop?
Okay, same button.
Same button?
Okay, see. Start, stop. 1.07 seconds. Reset.
Alright, good. Alright, that's it. Alright.
Everybody got it?
This means start and stop. That's it.
Okay.
Alright.
Then go to town, people.
Alright, so we going.
What I'm going to be doing
Alright, we'll do the passing first. How you measure this scale thing? Like 5, 25 on this
Okay.
old thing.
Okay. Okay. See, I've got it set at 5 degrees.
Yeah.
And it's the longer, lower one that measures degrees. When you go up, you'll put this part at 10, and then at 15, at 20, 25,
So
and
you
30.
rotate this
Yeah,
thing?
you loosen that, move it up, and tighten it back.
Okay.
Do all the measurements at 5 degrees with all 3 balls first.
Right.
Yeah.
And
Then move it up. Okay.
Alright, you ready? Okay, 1, 2, start. That's all.
I would suggest the same person who releases is, okay, get in the group.
Oh, you're in the room.
Yeah. No, okay. Okay, I'd say the person who releases it starts and stops. Because otherwise there will be a delay time before
So I'll
once you
be
release. Huh?
So I started and then he
No,
started.
I say the same person who's releasing it. And then when you hear it hit then or see it hit then, you stop it. So you're ready to go. Wait, we're in the track. Okay. I don't think she's a very good volleyball.
I'm not gonna go.
Okay, okay. I'm going to run down to my office and pick up the flash drive. I'll be right back.
I can have it. I can do this. Alright. Huh. This means start, stop, and then so you start. 1, 3, 2. Oh, average.
I keep do the same ball 3 times and then take the average the 3 times again.
Well, what's time? It's 1:32. Take it. Yeah. That's 1.32, right? I think so. Alright.
You do the same ball 3 times.
You gotta rise it up, I think.
Yeah, but we're gonna do like all 3 of them and then one right. Alright, yeah. 1.2. 5, 10. Alright. Middle now. Alright,
You gotta do the same ball 3 times. And then take the average of the 3 times you did the same ball.
This is the third one.
Okay, were there any questions?
This is Timmy.
Huh?
This is Timmy.
Yeah. Bottom, yeah, that's very Okay, any problems, any questions? And it is 3:45, so that means I mark the roll again. Okay. Zaria is still here. Austin hasn't made it in yet. Dominique, we lost, right? Demetrius is still here. Yeah, I see you.
What was the plastic one?
Samaya is still here.
Oh, okay.
Seth is still here.
Okay, wait.
The rubber one.
Francis is still here.
What was the plastic one?
Brett is still here.
The class,
The middle one.
the class.
Chris is still here. Shad we haven't seen yet. Bree is still here. Kayla's still here. Lonnie we haven't seen yet. Leslie's kind of here. Diego is still here. Renee's still here. DeAndre, I forgot to mark your name. So you're still here. Kelvin's still here.
Yeah, I'm still here.
Barely, okay. And Grayson's still here. All right, good deal.
Oh, wrong. Okay, someone kicked the bucket. Okay. Yep. I'm sorry. Okay. Choose whichever team you want to go with. Okay. They all have 5, so you'll be the 6th.
0.6 to average speed. We're on part 3.
Did you get a copy of the well? Did you get a copy of the well? Huh? This one today? Okay.
It's the last one. I got a question.
Okay.
So we got all the time.
Okay, wait just a second. Let me paste this.
Let me
Okay.
pay something. All right. So we got all the times here.
Okay.
So
Throw out the high and low and put the middle. Okay. You could have done this as you went along. Okay. There's the high, there's the low. Use the middle. You know, do that for each one.
use the middle is right here.
Yeah, whichever is one. Throw out the high and the low and use the middle.
Okay.
Yeah, for every one. Okay. Okay. If anyone gets to the point where you're got all your measurements, have you got there? Okay. Then let me explain what to do next. Y'all are probably onto it, but whatever. You all have measured the length of your ramp, right? Okay. So if your first column is completely filled out, the time column, right? Okay. What were the units for those? Seconds, exactly. Okay. Some of them were decimal seconds, right? Okay. Now, how do you get the average speed? No, okay, wait. No, okay. Okay. What I said to do, you could have, okay. When you were recording the things, did you write it on the back of the page or something like I said? Oh, you did. Okay. I said throw out the high and the low and use the middle. That's what you record there at the time. How do you get average speed then? Anybody? Distance divided by time. What was your distance? How long that was? You measured that on the first page, right? Divide that by the time you recorded on the second column, right? Or third column, whatever that is. Okay, and that will give you the average speed, right? So that's the calculation. Now, actually, if the measurements are through, if you want to, we can go back to the classroom, but if you just as soon work here, you can work here. I don't care. Y'all gonna stay here? Okay. Any questions so far? That gives you average speed. When you get all those done, stop and ask me, and we'll go on from there to the next one. Okay? Go. Yes, oh, sorry.
Are you on the distance?
What's that?
I
Okay, you
find my
didn't.
distance.
Didn't you measure it?
Oh.
Is that was to the nearest tenth of a centimeter?
Yeah.
Okay, let me see that.
Hey.
Okay.
Make 40 feet.
But you see, this is 40, 41, 42, 43, 0.7.
Point what? 43 point what?
Whatever you think. Okay, that's the distance. Divide that by the time that you have in the middle column, third column. Yes.
So the average speed is the velocity?
Second, average speed
Is the velocity? Yes.
Okay. All right. Okay. Now, this is a time for recall. Okay. I'm recalling all the left. No, that's not the count. Okay. You got average speed, or at least you're all working on it, right? Now, how do you get final speed? Remember, there was a second way to get average speed. And what was it?
The VL plus V1 divided by 2.
Exactly. Okay. Now, what was your initial velocity?
0.
0. And you got your average speed, so you have average equals 0 plus final, right? No, divided by 2. Okay? Divided by 2. Okay, are you following this, Millie? I wish I had a board in here. I don't. Okay? But let's see. Picture this now. Average speed, which you have, is equal to V final minus 0, which is just V final divided by 2. So to get what final speed is, double your average speed, right? Because the average speed, here's the concept of it, the initial speed's here at the top, your final speed's there at the bottom, so your average speed, which is what you calculated, is right in the middle, so double this and you get your final speed. Because this is uniform acceleration, okay? So just double the average speed, that gives you your final speed. Pretty easy calculation, right? Okay. Now, before you go any far beyond that, ask me. Let me know. Goodness gracious.